Hello everyone, and welcome to this lecture video that is going to tell you about acids and bases, and it is going to reference electrical conductivity of the solutions which we have previously discussed. So the first thing to talk about is what is an acid and a base. And generally an acid is defined as any compound that reacts with water to produce hydronium ions, which is written as H3O+. But is sometimes just written as H+, because scientists are lazy and they don't want to write all that out. H3O+ hydronium is a polyatomic ion. So it is a group of atoms that are bonded together that together have given up or gained extra electrons. In this case, they have given away an electron. So an example acid is hydrochloric acid, HCl, which reacts with water to produce chloride and hydronium ions. Bases, on the other hand, are compounds that react with water to produce hydroxide ions, which are on your list of polyatomic ions in your reference tables. An example of this is ammonia, which reacts with water to produce hydroxide and ammonium polyatomic ions. When you mix an acid and a base together, the hydronium and hydroxide ions that they create react together to form water. And this process is written as a double replacement reaction, and it is called a neutralization reaction. So here's an example of the acid and base reacting together to form water and potassium nitrate. So here is where the electrical conductivity comes in. Back in the days before chemical properties were available on the internet, and you could just go into Google and type what is the conductivity of a 1% ammonia solution. If you needed that information for, say, a homework problem, you had to go to the library and find the CRC handbook and hope that nobody else was using it, and look through the hundreds of pages to find a page with information about electrical conductivity. And it would look something like this. And you would really hope that the solution that your homework problem was asking about was listed on this page, because if it wasn't, you were kind of out of luck for that homework problem. So on this page, and others like it, you have a listing of compounds that can be dissolved in water. You have various concentrations of those solutions, 0.5%, 1%, 2%, 5%, and so on. And then you have in the table listed their ability to conduct electricity. So for example, if we're looking at ammonium chloride with 0.5%, you get a conductivity of 10.5. And then you add a little more ammonium chloride and you get a higher conductivity. And you add a little more and you get a higher conductivity. And you add a little more and you get a higher conductivity. And so on. So remember that electrical conductivity is created by having mobile charged particles. So when you dissolve ammonium chloride in water, it separates into ions, which can then carry the electrical current across the solution. And having a high electrical conductivity indicates that you have a compound who is very good at separating into charged particles, right? And we call that a strong electrolyte. So ammonium chloride is an example of a strong electrolyte. It is helpful to make concentration constant when you are comparing electrical conductivity. So generally, we look at the 1% by mass column on that page, and we call compounds with an electrical conductivity greater than 15 strong electrolytes. Ammonium chloride is an example of that. Sodium chloride is another example of a strong electrolyte. It has an electrical conductivity of 16. These are both ionic compounds, so we expect them to be strong electrolytes. Now, acids sometimes fall into this category of being strong electrolytes. For example, nitric acid at 1% has a conductivity of 56, so that makes it a very strong electrolyte. Other acids, like citric acid, don't meet that criteria. They only have a conductivity of 2.1 citric acid at 1%. So what's happening to these particles, right? An acid, by definition, when you dissolve it in water, it is reacting with water to produce hydronium ions. But not all of them are very good at that. So here's a list of common acids. Most of them are in your reference tables on page 2. Notice that acetic acid and citric acid have very low conductivities. And this is reflecting the fact that they are not very good at separating, at reacting with water to produce those charged particles. And so they are called weak acids. The other acids that are good, and the majority of their particles separate into charged ions, are called strong acids, just like we have strong electrolytes and weak electrolytes. Remember that strength is describing the compound and its ability to separate into charged particles, or in this case, its ability to react with water to produce those charged particles. In strong acids and strong bases, just like in strong electrolytes, most of those molecules are forming the charged particles, but in weak acids and weak bases, just like in weak electrolytes, very few of those particles are actually creating ions. Most of them are just kind of hanging around as neutral particles in the solution. Now, when you're trying to talk about acids and bases, and their ability to react with other materials, aka burn the skin off Mr. Barton's fingers, just talking about their strength or just talking about their concentration doesn't do a great job of describing their ability to burn your skin off. And so in order to do that, scientists decided to focus on the hydronium ions. Right, because those are the active agents. Those are the ones that are reacting with Mr. Barton's skin and causing the chemical reaction. So when a scientist talks about the reactivity of an acidic solution or a basic solution, they're going to be focusing on the description of the concentration of hydronium ions. Now, these concentrations tend to be very small, even in dangerously acidic solutions. And so scientists are not interested in writing out really long numbers. So instead, they describe the acidity of the solution using pH, which is a shorthand for the concentration of the hydronium ion. And it is focusing on the power of 10 of that concentration. So if you had a solution whose concentration of hydronium ion was 1 times 10 to the negative 8th molar, instead of having to say 1 times 10 to the negative 8th molar hydronium ions, the scientists would just say pH 8, which is much faster to say and to write. But what does pH actually mean? So P stands for negative log, and then the H is for hydronium ions. So if we had a concentration of hydronium ions of 1.5 times 10 to the negative 7th molar, and we need to know the pH, we would get out our calculator and we would type negative log 1.5 times 10 to the negative 7th, close our parentheses, press enter, and it would tell us what the pH of that solution is. You can also do the reverse calculation. So if you know that your solution has a pH of 5.4, you are able to calculate the concentration of hydronium ions by doing the opposite process of a log. And the opposite process of a log is taking 10 and raising it to the power of your pH. In this case, you do need to make it the negative pH, right? Because pH has a negative inside of it. So in order to undo it, you're going to need to put another negative in there. So if we wanted to find the concentration of hydronium in a solution that has a pH of 5.4, we would take 10 and raise it to the negative 5.4 power. So having established pH, scientists can use it to describe a whole range of solutions. The most acidic compounds or solutions have larger concentrations of hydronium, concentrations that are closer to 1 instead of being a tiny decimal. And so the most acidic solutions have the smallest pH values. The flip side of this is that bases do the opposite. So if you have a solution with a large pH value, that means it is very basic. Now, both ends of this pH scale can burn you. Drain cleaner and hydrochloric acid will both take the skin right off your fingertips. If you want to stay safe, you need to stay in the middle with water right at 7, and that is considered neutral on the pH scale. Milk and blood are other solutions that are close to neutral, so they won't burn the skin off your fingers. Now, pOH is another way to describe the acidity or basicity of a solution. It is focusing on the concentration of the hydroxide ions produced by the base instead of focusing on the concentration of hydronium ions produced by the acid. pH and pOH are related, right? Because each hydroxide ion will react with the hydronium ion to produce water. So the sum of the pH and the pOH is always 14. So if you know the pH and are looking for the pOH, you take 14 and you subtract out the pH of 6, and that will tell you the pOH, which would be 8. So with the pH and the pOH, if you have one and are looking for the other, you take 14, you subtract out the one that you have, and that will give you the one that you are looking for. So some example calculations. If you, just like with pH, if you are given the concentration of the ion and are asked for the pOH, you take the negative log of that concentration, and that will tell you the pOH. So if your solution has a concentration of hydroxide of 1.5 times 10 to the negative 7th molar, you would type into your calculator negative log 1.5 times 10 to the negative 7th, close parentheses, equals, and that would tell you the pOH of the solution. You can also do the reverse calculation. In order to undo the P, you take 10 to the negative pOH. So if you were told the pOH was 5.4 and you were asked for the concentration of hydroxide ions, you would type into your calculator 10 to the negative 5.4 power, and that would tell you the concentration of hydroxide ions. One of the most complicated versions of this calculation question that they can give you is to give you the wrong P for the concentration that they're asking for. So for example, if they tell you the pH is 5.4 and they ask you for the concentration of hydroxide ions, which would be really easy if they gave you the pOH, you have to find the pOH first. So just like I said earlier, in order to find the P that you are missing, you take 14 and you subtract out the P that you have. So 14 minus the pH of 5.4 would tell us that the pOH is 8.6. Once we have the pOH, we can undo the P part by taking 10 to the negative power. So we'll take 10 to the negative 8.6, and that will tell us the concentration of the hydroxide ions. So this lecture video talked to you about acids and bases, what they are, how we talk about their strength, and also how we talk about their ability to react with other compounds using pH and pOH. Thank you very much and have a nice day.